Thanks very much, Ryan. So I have great pleasure in introducing two people who are interested in neuromodulation. And we're going to have a fabulous conversation about consciousness and how you modulate it and ideas of where it comes from. So there's Divya Chander, who is Chair of Neuroscience and Faculty of Medicine at Singularity University, and actually was a finalist to be an astronaut in 2004. So she's interested in space too. And then Jay Sanguinetti, who is an adjunct professor at the University of Arizona and a research professor at the University of New Mexico. So we're going to kick off with a fascinating conversation. Divya, over to you. She's going to do a slide presentation and talk about her interests and subjects. Is it all working for you, Divya?
Okay, well, good morning, good afternoon, and good evening from wherever in the world you are watching us. And thank you so much for being here and sharing this time with us. I'm going to be talking to you about what I actually see as one of the most fundamental problems in all of science. And that is the problem of what is consciousness and where might it come from? And one of the problems we've had in the scientific community with talking about consciousness or measuring consciousness is it's incredibly difficult to define. It's difficult to describe the contents of our awareness. It's difficult to generate hypotheses when you can't define something well. So what we have been doing through history is defining the contents of our conscious awareness. So for instance, when a human retina captures light at 670 nanometers, I have the sensation that I have just perceived the color red. And the question is, when your eye binds 670 nanometers of light, your photoreceptors, do you also see the same red that I do? Now, historical philosophers have been working with this problem for a very long time. Here you even see a quote from Sir Isaac Newton in a letter that he wrote to Sir Henry Oldenburg, approximately 1672. To determine by what modes or actions light produces in our minds the phantasm of color is not so easy. And it isn't so easy. In fact, this approach is quite difficult because, again, it relies on describing the contents of our conscious awareness. So perceptions that are formed, temporary contents of working memory, where you actually put your attention. But there are other ways that one might actually be able to start to define what consciousness is. And that's the approach that I and some of my colleagues have taken. We are all neuroscientists by training, but many of us are also clinicians. That means we take care of patients. And we've been taking care of patients that naturally or artificially through drugs are expressing things that we all seem to agree on as a community are depressed states of consciousness. And those states include things like sleep, as you see here, being anesthetized, or in fact, even being comatose. Now, the way we do that is we take all of these states and we map them. We map them using a lot of different kinds of techniques. Here you see mapping a brain connectome, which is kind of an anatomical technique. You can use things like the electroencephalogram, you can use MRI, you can use things like PET imaging, ECOG, where we put electrodes directly on the brain. But the end result is the same. What we're trying to do is see what brains that are fundamentally more conscious, more awake, and more aware look like, and then compare that to depressed states of consciousness and see what that sort of difference is. Now, going back to what I do, I became an anesthesiologist for a very important reason. Anesthesia, the major target of our drugs is the central nervous system, something we call the central neuraxis. And as you see in this image, it's a brain and it's a spinal cord. And think about this. If these anesthetic drugs didn't exist, modern surgery today would not be possible. We give humans drugs that make them blissfully unaware of a surgeon's knife. And we use our drugs and they bind to receptors in the brain in order to reversibly dissolve conscious awareness. And then when surgery is over, we wash those drugs out of the system and then we bring you back to awareness. Now, what I do in the operating room, as you can see, is I actually measure this process of losing and regaining consciousness in humans in real time. And as you can see in this image, the the patient actually has a set of electrodes on her forehead. And over my left shoulder, you can see her brainwaves in real time. So I actually follow her brain in the operating room, and I'm watching as she goes from being awake and aware to losing complete awareness and then coming back as my drugs basically are washed out of her brain. Now, one thing I can do with this is actually create what I call the Goldilocks zone for her brain. So I don't have to guess what her brain needs. I don't have to worry that she's going to wake up during surgery, because I can tell by the oscillations she won't. But as surgery progresses and we're getting towards the end of a case, I can also make sure that I'm lightening her up sufficiently so that when the surgery is over, the drugs come out quickly and I can bring her back. Now, what's interesting is that a lot of people think that when we induce unconsciousness with anesthetic drugs, the brain becomes electrically silent, but that's actually not the case at all. In fact, what happens is the brain becomes even more synchronous. So what do I mean by that? It means that if I'm measuring those electrical waves coming from the front of her head, they look really similar to the waves coming from the side and from the backs of her head. And this process, this idea of being hypersynchronous, actually marks something else. It marks a reduction in information processing capacity in the brain. In other words, when your brain becomes more synchronous, it actually calculates less information. And interestingly, this is one of the theories of consciousness and unconsciousness, that when we have depressed consciousness, we actually cannot calculate as much information. And that's a theory that's notably been put forward by Giulio Tononi and Christoph Koch. Now, there's another theory of consciousness, and this has been basically defined or described by active measurement. And that is, if you put somebody, say, in a scanner, an fMRI machine, or you measure the electrical activity coming from their brain, and you see what happens when they're awake and aware and when they have a depressed level of consciousness, it seems as if their brain is almost literally broken apart. It's become somewhat functionally disconnected. Right now, as I'm talking to you and as you're listening to me and we're engaging, our brain is a series of discrete modules, and they're all kind of chattering amongst one another. They're not that synchronized. But as I, for instance, get drowsy and fall asleep, or if you give me anesthetic drugs, those connections actually break in my brain. So functional disconnection, that's another way to characterize losing consciousness. Finally, one of the ways that we recently published on and defined is that brains that are less conscious actually are less complex. And what do I mean by that? It means that if your brain, when you're awake and aware, has a number of choices or a number of directions it can go in, as your consciousness becomes more and more depressed, your brain does not seem to have as many choices available to it. It can't make as many decisions. It can't go in as many directions. So this is another way, complexity of defining conscious versus unconscious brains. Now, ultimately, we have been measuring this sort of functional disconnection or this change in complexity through all of these different states. And even as I'm describing this to you, you might say, wow, that's kind of interesting. So you can describe brains that are less conscious, but can you actually tell me where it comes from? And that's not such an easy thing to do. Now, some people believe that perhaps if we could build a full simulacrum of a brain, so for instance, we could model every single neuron, every single connection, the things that we call synapses, we would somehow come to an understanding of how consciousness arises. And there are groups working on this problem. This is basically a simulated chunk of brain, a little tiny volume of cortex that's been created in silico, in a dish, on a chip. And you can see these neurons are actually firing and producing something that looks like a real living organism's electroencephalogram. But again, all created in silico. And this idea that modeling the brain, building it, this sort of reductionist idea that we will be able to come to an understanding of how consciousness arises is something that even this gentleman thought would be possible. This is Francis Crick. Now, many of you would know Francis Crick because he actually won a Nobel Prize for helping to define the X-ray crystal structure of DNA. But in fact, later in his life, he turned to neuroscience, and one of his his goals was to try and define and understand consciousness. And he essentially felt that it was a reductionistic problem, that if you could understand every component of a brain and rebuild that, you would build something that expressed consciousness. But he still never said what that was. And again, to philosophers like Dave Chalmers, this didn't explain the hard problem of consciousness, which is what persists even when the performance of all relevant function has ceased. So I'm going to propose to you a maybe somewhat heretical idea, and it's something that not all neuroscientists share, but bear with me, I'm going to take you on a journey. What if consciousness were not produced by the brain at all? What if it weren't an epiphenomenon of this complex system? What if consciousness were something that brains accessed in the natural world? So for instance, it could be a description of the total information available to us from the physical universe. And that would be consciousness with a big C. And that part of the information that was received by our brain, filtered and processed, that would be consciousness with a little c. That thing that finally produced the percept, that basically allowed us to hallucinate our visual world in order to survive. So let's appeal to the visual system as an analogy, because it's much easier to understand that way. So here you see a human, and you can see that we as humans, we have 3 color receptors, and this allows us to bind enough information in the electromagnetic spectrum to perceive a rainbow, moving from red all the way up to violet. So 3 receptors. Now this guy over here, this mantis shrimp, actually has 12 to 13 color receptors. And as a result, this shrimp can see a much wider swath of a rainbow than a human can. They can actually see into the infrared all the way into the ultraviolet. Now, what's interesting is you could just argue that it doesn't really matter, because what we need as a human is basically what our 3 color receptors can pull in and bring to the back of our brain, this thing we call the visual cortex. Now, just remember, all this information coming in from the electromagnetic spectrum, that's not what we're actually perceiving. We're seeing a really impoverished version of what's initially available to us in the universe. But the information that we do see, that we do process, that we do perceive, is what's allowing us to survive in our ecological niche. And so we would say that even as our brain is processing visual information, it's not producing that visual information. In fact, the visible spectrum is a property of the universe and not our brain. Our visual perception, essentially, it begins in the world, but it ends in our minds. Now, there's another way to even think about this. What about all that information available in the universe, and how much is actually available? So there's a physicist from MIT by the name of Seth Lloyd, and he tried to estimate this. And the way in which he did this was he tried to imagine the universe is about the size of a black hole with its event horizon going out to the edges of our known universe. In doing this, he estimated the size of the universe, the information being about 10 to the 90th bits. Now, that's a huge number. It's so much more than all the grains of sand on the earth and all the stars in the universe. But within this really large swath of information, if we had to evolutionarily create a brain that could perceive all this information, that brain would immediately burn out. And in fact, what's happened, humans, mantis shrimp, is that we have evolved a reduced set of circuits that can bind just enough information to survive in our ecological niche. And then when we actually measure the activity, the electrical signature of the brain in something like an EEG, we're essentially measuring that reduced version of what we're perceiving from the universe. And if you think about this, that would make the production of consciousness and the way that I'm describing it analogous to what the visual system does, but just on a much grander scale. The brain's visual system reduces the available information to a visual percept. What if consciousness itself were not produced by the brain, but it were simply a reduction of the available information in the universe to a conscious percept? So in this worldview, consciousness, again, with a big C, becomes a way of describing the total information available to us in the universe, while consciousness with a little c, is the hallucination created by our brain for us to act on what's necessary for our survival. And it becomes a function of, in fact, sensory integration, like most of the sensory modalities in our brain. And what that also means is that the brain here is acting as one enormous information receptor and processor. And that also by necessity means that we may not have discovered all the ways in which our brain can bind information from the universe. It may be beyond things like our visual system, our auditory system, and our somatosensory system. And in fact, I've thought often about what alternate possibilities are. In fact, there is even the possibility that our brain, even though we measure it in terms of classical physics, may also display some quantum characteristics that are really difficult for us to measure right now. And so this brings us back to that heretical question. What if consciousness were not produced by the brain, but merely the name that we give to the filter for it? And it's a very reductionist filter. Now, that brings up some interesting possibilities. Imagine this, if the brain is a filter and now we change those nodes in the filter or the functional connectivity of domains of the filter through things like that exposure to anesthetic drugs, would that fundamentally alter our access to information? In fact, you could say that paradoxically, in fact, our access to information in the universe might even increase, but because we don't have explicit recall under anesthesia, that increased access to information might be wholly unremembered. You might imagine something similar happening through the process of meditation, or even to rewire the filter using things like psychedelic drugs or learning and different kinds of experiences. So I would argue that that's a good explanation for how the nature of consciousness is changed through our perception and through processing through an individual brain. And it brings up some other really interesting questions. So for instance, can an artificial brain or an increasingly complex machine ever truly express consciousness? And not because consciousness is some ineffable quality, but because their circuits have now become sufficiently complex to allow them to access a universe of information that was not previously available. And in fact, you know, it's going out on a limb, but people often wonder, does that mean that we could eventually upload the information that is our brain? That rests on something that I call non-local consciousness. What happens if an organism dies? Now, if your consciousness dies with it, it's a bit unlikely that you could move it around. But if consciousness persists as information, much as the visual spectrum outlasts the visual system that perceived it, you could almost imagine that consciousness could be potentially moved from body to body, or from body to a computer, or from avatar to avatar. More fundamentally too, and we're going to take a little bit of a turn here, all these things that I'm describing, this idea of mapping consciousness, it does something else really important for us. Studying human consciousness provides a template for understanding or recognizing consciousness that differs from our own. And here the example I would give you is that of potentially other intelligent species on this planet. Now, there are only a few ways that we can actually mark intelligence. One of them is through direct communication. So for those of you who have heard of Coco the gorilla, she was taught sign language, and we could directly communicate with her. And that was a window into her brain, into her level of intelligence. But more often we do this indirectly by observing behaviors in other animals. The third way we have available to us is by mapping their brains and reading what they directly want to say. And some of the techniques that we use for signal processing in the brain could assist us in this domain. And the kinds of animals I'm talking about is like things like octopi. They're believed to be incredibly intelligent. To my knowledge, we have not been able to sign or communicate with them. But this would be a really interesting approach. Other clearly intelligent species include our closest relatives. And again, we were actually able to directly communicate with Coco, and she also had a partner. But brain mapping may be another means to do this. And in fact, several animals express a form of self-awareness that seems to be associated with with sentience or consciousness. One of them is this idea of mirror recognition. Can an animal look in a mirror and in fact recognize that this is their self and not another member of their own species? Now, mind you, human babies cannot do this initially, and one might even argue that animals like dolphins actually have mirror recognition long before human babies do. And there's a beautiful example of it here in this video. So if you take a dolphin and you put a spot on their belly in a place they can't see it, but you put them in front of a mirror, they know that this is themselves. And in fact, they sort of play and prance in front of the mirror in order to get a better look at this spot. So they have this sort of sense of self, and they even have a sense of their embodiment and that this spot is part of them. I'd like to, as we close, introduce one last idea to you, and that is we might be able to use similar techniques for understanding neural signals in the brain to understanding and exploring the possibility of intelligent life in our universe. And that happens to be one of the core missions of something called SETI, or the Search for Extraterrestrial Intelligence. Their core mission is to explore, to understand, and explain the origin and nature of life in the universe and the evolution of intelligence. But I would argue that consciousness has to precede that intelligence. And it would very much help us if we could recognize the variety of forms that life would take with some of these techniques that we have developed for understanding neural networks. So with that was a lot this morning for me. And I wanted to say thank you all, and please be in touch if any of this was interesting for you, or if you want to talk more about this. Thanks.
Thank you, Divya. That was a fabulous talk. It really appeals to me. I believe in all the idea that we don't know half of what we're possibly able to understand and perceive. So we'll have lots of discussion about that. Jay, over to you next, and then we can talk about it at the end, all of us.
All right, thank you. And yeah, thank you for that fascinating talk, Divya. That was really interesting. Great introduction. Okay. So I just wanted to give you a couple slides introduction to some of the technologies, the neurotechnologies that are being created to attempt to alter and enhance consciousness. Now, as we all know, we are dealing with multiple epidemics. We have issues in the United States, at least, with chronic pain and addiction on opioids. We have an increase in anxiety and depression, as well as suicidality. And we're in a really interesting situation where we've been developing these tools to map the brain using things like fMRI and EEG. So we have about 30 years of information where we're starting to get a sense of what a depressed brain looks like, what an addicted brain looks like. And yet the neurotechnologies that we've created have yet to really significantly reduce these problems on a global scale, on a massive scale. And so what I wanted to do is give you just a bit of an introduction into some of these technologies so we can discuss those in the discussion sections. So most of these technologies involve a notion called Neuro Modulation, which is any technology that acts directly on nerves. So you can modulate any nerves in the body using various forms of energy like electricity, typically. But if you really want to talk about attempting to address some of the global problems like the rise in depression and anxiety, really you got to start thinking about modulating brain function specifically. And so the typical way to do that, which has been used for the past 70 years or so, is actually to do an invasive surgery. So you drill a hole in the brain and you dip an electrode down in. So I'm not sure if you can see my cursor here, but that's an electrode that's been put into the brain of a human patient. And you can actually stimulate or modulate specific areas of the brain to change consciousness. Now, in these cases, it's usually to treat something like Parkinson's disease, but you could also treat depression with this. Now, it turns out most people don't like to have holes drilled in their brains. And so what's been developed over the past 20 years or so are technologies that are considered non-invasive, meaning you don't have to drill a hole. You wear some type of device on your head and it puts some type of energy directly into the brain to modulate brain function. So I'll tell you just briefly in about 5 slides about these different technologies. Now, believe it or not, pretty much any form of energy can be used to modulate the brain, from magnetic fields to electricity, and then on down to light. You can actually use about 820 nanometer light to change the mitochondrial process in the cell. And what I really specialize in is using high intensity sound, or low intensity focused ultrasound to modulate brain with mechanical energy. So any of these modalities can alter brain function. They do it in different ways. Now, the most, I guess, powerful device that's been created for non-invasive neuromodulation is called transcranial magnetic stimulation. This involves a very strong magnetic field that's put on top of the head, and you can actually induce very tight electric fields in the brain. Now, this device has been well studied. There's probably thousands to tens of thousands of papers at this point. It's been FDA approved to treat depression, and it works just about as well as Prozac for depression, and it has very few side effects. So it has huge benefits over pharmaceutical interventions. The problem is it's very expensive. These devices are $50,000 to $100,000, and you have to do them in the clinic. So you can't get one of these at home, which really prevents the scaling of these devices out into the public. Now, one device that you can get at home is called transcranial direct current stimulation. This is basically hooking your head up to a 9-volt battery. There's a couple batteries in this device here. And this puts a little bit of current over your scalp, and some of that current gets into the brain. Now, there's definitely been tens of thousands of papers on this technology. There's lots of science. And you can scale this out. You can make these devices for about $100. But the science is relatively weak, in the sense it's hard to replicate these studies. It's been kind of unclear what the mechanism is of these devices. And that's really because if you look at what's going on in the brain, the electricity from the pads actually spreads all over the brain. So you can actually see where the pads would be on this person's head. And now we're looking at where that electricity is going. And you can see that that's a lot of neurons. That's tens of millions, hundreds of millions of neurons that are getting targeted there. And so it's very hard to control this type of technology and really get a reliable effect in the brain. So it's really, that prevents it from scaling out to being a very useful technology. TMS, on the other hand, magnetic stimulation, can be very focal, but as I said, you can't get these devices in the home just yet. And so it's really preventing us from scaling it out to the public to give us a targeted technology to treat things like depression and anxiety. So several researchers have been looking at other technologies that can get around some of these issues. What you really want is, you want low energy, you want it to be safe, you want it to be focal, like I'm showing here, and you want it to be able to be eminently scalable. You want the technology to already be available. And so ultrasound is actually one type of technology that fits all of these categories. As you can see here in the monkey brain, this is an ultrasound beam that can be focused to a very deep part of the brain, and it's very focal and reliable in targeting the brain. And these ultrasound transducers are very well studied. Ultrasound is a very developed technology. And so if you can modulate the brain with ultrasound, which it seems like we can, then you can eminently scale this out to the public, to clinics, to hospitals, and you really have a new sort of avenue for clinical research, and then potentially making technology that the public can use as well. So now just continuing a little metaphor here. So with focused ultrasound, you can see it's another magnitude of focality. So this really shows the power of transcranial ultrasound over what's already out there and available. And so with that, in my lab, we've been thinking about combining focused ultrasound with interventions that we already know can enhance brain function, like mindfulness training, as well as interventions that can be used in the clinic, like cognitive-based therapy, that it's useful for things like depression and anxiety. And so the idea is basically making a very simple ultrasound device. So that's what you see here. It's guided by MRI in this case, and that's the subject's brain. And in the case with mindfulness, what we're finding is that over a several-day course, we can actually boost the effects of mindfulness training, which has huge benefits both in the clinic. Mindfulness treats things like depression and anxiety, as well as being used by the public. If we could get mindfulness out to the broad public, we could start helping to reduce things like anxiety and depression, which are clearly on the rise after the events of 2020. And so this is what the device looks like in our lab so far. We're using electroencephalogram EEG to read from the brain, so we're doing neuroimaging. And then we have a pretty clunky looking device here with the ultrasound transducer on the back, but all of this can be shrunk. This is all definitely wearable, so the patient or subject can take this home. And then the system can both read and write from the brain at the same time to get to the sort of next level of intervention over the technologies that are created so far. And so this is just one example of these technologies. There's several other types of technologies that are on the horizon that are, you know, the typical saying is they're 5 years away. That's what we say in science. But definitely there's other technologies like this that are coming that will allow us to target the brain with more focal specificity. So really getting into those brain networks that Divya was talking about and being able to regulate those on an individual basis so we can actually try to scale some of this technology out to the public. And that's all my collaborators there. So I think now we're going to open this up to a bit of a discussion.
Jay, that was wonderful. Thank you. So both of you touched on, you know, neuromodulation. Well, Jay, yours was all about that. What do you think about meditation? Because the Dalai Lama inspired you, didn't he? He was talking to a group of neuroscientists and said, how can we assist meditation in being, in a sense, a quicker process? And
yes.
Do we think that meditation is a really good form of treatment, or do we think it's an accessory form of treatment? What do you both think?
Sure, that's a good question. I'll take the second question first. So the science is growing rapidly on meditation research. As everyone knows, there's hundreds and hundreds of studies coming out every month. But most of what we know is on an 8-week course of meditation. And with that 8-week course, we know that that can, to a mild degree, reduce symptoms of depression, anxiety, chronic pain. It really does seem to reduce suffering on a sort of broad scale, as has been argued by Buddhist meditators. But the longer term effects, the sort of things that we're really interested in the lab, we're not interested in mildly reducing pain. We're interested in using technology to really dramatically alter someone's sense of happiness, their sense of purpose. You know, we want to help people deeply transform their lives. That's the promise of mindfulness and meditation. And the science isn't clear on that yet. If you talk to a long-term meditator, they will tell you their life has been transformed. It's not just their minute levels of pain have gone down. They're significantly happier people. They have better relationships. Everything has changed in their lives. So the science is not there yet. That's where we're trying to get in our lab. We're trying to use some of these technologies to accelerate some of the practice so we can help people experience and taste those types of transformations sooner.
Yeah, totally.
Yeah.
So coming on to what Divya talked about, which was the idea of the brain being a receptor for events outside the brain, in the ether, as it were, what we call the ether, and being an enormous processor. We now know that there's an eye in the middle of the brain called a chrono eye, which is an addition to the receptors in the back, which help with the clock. How would you postulate, we're really taking it outside what we know now, that the consciousness is received? What type of receptors could possibly be that then enter the processor, which is the brain, and get, you know, sensed, as it were? Do we have any idea?
So we don't, beyond the receptors that we have thus far defined. So this chrono eye you described, there are alternate pathways by which energy, in this case photons, can get into the brain and modulate the brain. And in this case, this kind of modulation typically affects things like our circadian cycles and whatnot. As Jay is finding out and talking to us about, light might even be able to enter through, not just through your eye, but through other means, and actually modulate even things like the mitochondria, which are the energy factory houses within our brain. Do we actually know what other receptors might exist to actually bind information?
I don't yet have an answer to it. And the thing that I like about potentially describing a theory is that it can generate some hypotheses that can be tested. I do believe that once we get to the point where we can begin to measure things on a quantum level, we might find some other interesting kinds of processing going on that we don't describe well now. And, you know, for a long time, the brain was not thought to potentially engage in quantum processing because it's a warm, wet environment, and quantum processes were not thought to exist in those places. But in fact, recently we've been finding things from the physics world that, for instance, photosynthesis has several quantum processes. And that takes place in a similarly warm, wet environment. And if that's possible, it's potentially possible for the brain as well. By the way, just in response to what Jay said to the last question, I want to 100% echo not only everything he said, but to say that I truly believe that meditation is a form of neuromodulation. And whether or not we've exactly proven what the outcomes can be for well-being and happiness, it just takes a lot more discipline to rewrite your brain, to rewire your brain through a process like meditation. And things that Jay's offering, like focus ultrasound, or people who've taken psychedelics, it's a bit of a shortcut, right? But if you looked at the filter that I presented, it 100% is rewiring the filter, whether it's in a given moment or it lasts. And you can quite imagine how that would change information processing. So I want to link it back to this question you just asked. It's not even just about the ability of the brain to bind information as a receptor, but how it ultimately filters and processes that information.
So when you're talking about the change of the information processing, I know this is something people who take psychedelics talk about, is do you think one needs a guide or a shaman to direct the processing in a positive way rather than it being, you know, too quick and a bit catastrophic? What do we both think? What do you both think?
Do you want to take that first, or should I?
Sure. I do think so. So if I had a little more time, I would have outlined the network in the brain that we're targeting, which is called the default mode network, which is really thought to be a core system involved in self-identity, self-processing, the sort of ego. It's not the ego center, because we can't say that yet. We don't quite know where the ego is, if it is anywhere. But when you take something like a psychedelic and they actually do this, they give people things like psilocybin, magic mushrooms, and they put them in an MRI scanner. I don't know how people can sit inside of a scanner and trip their minds out, but people have done this, mostly in London. And when you look inside the brain, you see that ego part of the brain, the self part, is completely disintegrated. That network that Divya was talking about is just not online. The more you take that off, the more that's correlated with spiritual experience, or mystical experience, as they call it in the lab. And so I think the more that you turn that thing off, the more mystical you have, the more likely you need something like a guide there. Because the self is evolved for a reason. It's there to help us guide our actions in the world, especially in a world like we're dealing with today. And so as you mess with that core system, that core filter, as Divya is talking about it, things can become unstable, and it's not always, you don't always have a God experience or whatever you want to call it. Sometimes you have a very bad experience, a bad trip. So that's true for psychedelics. That's also true for the technology that I'm creating and others like me are creating. And so that's why our technology is always used in the clinic right now. We always have an MD and a psychiatrist available. And on the retreats that we're doing, we always have a meditation expert there as well to help guide the person through these experiences that they're having, so they can do what's called integration. They can take these very altered states and they can integrate them in their body, so they can go back in the world and they can be a better father, a better mother, a happier, person, those types of things. So it's crucial, actually, I think, to have a guide.
Okay, that sounds fantastic. And is there anything that either of you picked up in each other's talks that you want to extrapolate on? The extraterrestrial thing. Jay, do you believe that the extraterrestrials have? I do. I believe in ghosts. I believe in ESP. I believe in the whole lot. But Jay, do you?
Do I believe they're out there?
Well, thinking with a consciousness.
I do. You know, my dream was to be an astronaut as well. I'm in amateur astronomy societies. I'm in Tucson, Arizona. We have very dark skies. So I look for aliens all the time. I would love to see a UFO. I do believe that advanced societies have to get past a threshold to survive, and I actually think we, humanity, are going through that moment. We've developed nuclear weapons. We're very close to using them on each other for the last 100 years. So I think all advanced societies go through that tipping point. And if they get there, they survive. And so I think if we find aliens, they're probably much more advanced than we are, because they've created all of these hyper technologies. They've gotten to the point of realizing that they're all one and everything is stardust. And I think when they get to that point, they survive. It's possible that lots of other alien societies have not survived that point. So yeah, I think if we find them, they're going to be so advanced, we're probably not even going to understand their consciousness.
It's interesting that you equate technology with advancement, but some people would think the tipping point was self-destruction. And I noticed that a member of the audience has asked about Elon Musk's Neuralink. What do you both think?
I think that Elon is trying to, by the way, Neuralink in its current incarnation is doing something that basic science and clinicians are doing, which is they're trying to restore function to people, for instance, who are paralyzed and things of that nature. So they're kind of following in the footsteps of a lot of that research that's gone before them. Ultimately, this idea of connecting humans to computers, to the internet, things that, by the way, have already been accomplished to some extent. Paralyzed people are paralyzed from the neck down, can control to some extent their interactions with the internet using their brain, because they can actually control parts of the external world, basically these things that are, I guess you could call them actuators, mice and keyboards and things of that nature, because these chips can actually translate their desire to move. They're actually intercepting these signals. Now, Elon ultimately, I'm not 100% sure he's interested in inducing the kinds of spiritual experiences that Jay is perhaps speaking to, which I think would help to evolve us as humans and maybe develop our empathy. I think he's looking at the raw increase in potential computational power that might be enabled by this kind of merging. And by the way, that is also a very much possibility. If you think about one of the definitions of consciousness that I gave, that we have from observing brains, it is information processing capacity. Once you augment that capacity by, for instance, altering the brain through things like brain-machine interfaces or neuromodulation, you have potentially increased the brain's information calculating capacity, and by that definition, very much potentially have fundamentally altered and potentially expanded human consciousness. In a good way, not necessarily sure, but the ability to perceive, bind, and process information, yeah, that's bigger.
That's absolutely brilliant place to end. Thank you so much, Divya and Jay, for a fascinating talk.
Yeah, thank you.
Amazing.
Hello, Ivan.
Amazing. Hi, Alison. That was an amazing talk and panel conversations. And I think I'm just going to bring it all to a close to say actually modulating consciousness is a fascinating topic, and actually possibilities we've had are huge. So thanks everyone for listening and paying attention to kind of the panel, and everyone from Divya, Alison and Jay for kind of all your contributions. The next session will start promptly at 6, and that focuses on insights and collaboration and designing for a better future. Hope to see everyone next.
Want access to more CogX videos? Subscribe now for free at cogx.co.